Okay, so we're going to try to go quickly through section 6.2 star and 6.3 star. So this means don't read section 6.2 and 6.3, read section 6.2 and 6.3 star. Okay, so this starts with a definition. The definition is the natural logarithm. Okay, so this is defined by an integral, and it is the following integral. So this function. So this is the natural logarithm or we usually just say log x, okay? Log x. We don't say ln, okay? Don't say ln x, okay? Don't do that. No ln x. Say log x. Log x. Say it with me. 1, 2, 3. Log x. Okay, this is the natural logarithm of x. So what is this? It's defined by an integral. Here's what the graph of 1 over t looks like. Okay, so this is t. This is 1 over t. Here's the point 1. Of course, that goes up to 1 on the x-axis, or on the y-axis. So this is the area from 1 to x under this graph. Okay, so right there, that area is log x. Okay, this is the definition. All right, so what do we know immediately by the fundamental theorem of calculus, which we just got done studying? We know that the derivative of log x is just 1 over x, okay? Right? The derivative of a function defined by an integral is just take the variable, put it in here, that's your derivative. Okay, so we have some laws for logarithms. The first law is, some of these are going to look probably familiar to you. If you take the log of a product of two things, this is equal to the sum of the logs of them. Let's see. Well, wait, before we do two, let's just really quickly go through a proof of this, okay? Just a very, very quick proof, all right? So this is, right now, I'm writing down something which is a super bonus proof. So understand this proof. I'm going to ask about it probably on upcoming exams. So here's how it goes. If you take the log of a times x, so a is any number, and we take its derivative, well, let's use the chain rule here. What do we get? We get 1 over ax because that's what's inside of the log. We take the derivative, and then we multiply by the derivative of what was inside, so we get a, so we get 1 over x. But notice that this is also the derivative of log x. So these two, the derivative of log of x and the derivative of log of a times x, they're the same, and so that means the functions differ by a constant. So that means that log of a times x is equal to log of x plus some constant, okay? Anytime two functions have the same derivative, then they're basically the same function except one of them has a constant added to it. So what is the constant? Well, if you plug in x equals 1, all right, well, what is x equals 1? That's putting a 1 here. So you have the integral from 1 to 1, so no area, so that's equal to 0. So we get log of a is equal to 0 plus c, right? And so that means log of a is the constant. So in this case, we get log of ax is equal to log of x plus log of a, and that's our rule. Just make a equal y. Okay, so we make a equals to y, then we get this. Okay, so this is the proof. Usually when we write a proof, we put a solid little square at the end of it. Understand this proof, give you some bonus points on the next exam. Okay, we have other laws of logarithms at our disposal. The next law is let's see, so the log of x over y is equal to the log of x minus the log of y. And then another property is the log of x raised to any exponent is equal to the exponent times the log of x. Okay, so let's do an example using these rules. Express the log of a plus 1/2 the log of b as a single log. Okay, well, here's the solution to this. So we get, well, log of a and log of 1/2 log of b, get this. So let's use this power property number 3. Let's pull that in as a power. So we get the log of the square root of b, because bring the power in, so it would be b to the 1/2, that's square root of b. And then we use the property from the previous page where we combine these two, so this is log of a times root b, okay? That's all there is to it. All right, so let's graph log of x, okay? So some properties of the log of x. In order to graph it, we know that its derivative is 1 over x, which is always positive. Remember the domain, so the domain of log x is all x values bigger than 0. So this is always positive. The second derivative of log x is just the derivative of the derivative, so that's minus 1 over x squared, and this is always negative, okay? So what does this tell you? So the first part tells you that, that log x is increasing, not f, log x is increasing, and the second part tells you, since its second derivative is negative, it's concave down. Okay, so there's one property of its graph, another property of its graph. Another property that we already saw is that it passes through the point 1, 0, because the log of 1 is equal to 0, because there's no area under the graph of the function that defines the log. And then we have a couple of other properties, and that is the limit as x goes to infinity of log x is equal to infinity, and the limit as x goes to 0 from the right of log x is minus infinity. Can we see that? We can see that, okay. So we're going to combine all of these. So it's an increasing function, it's concave down, it passes through the point 1, 0, and it has these limits. It goes to infinity as x goes to infinity, it goes to minus infinity as x goes to 0 from the right-hand side. So if we graph a function that looks like that, it looks like so. So there's 1, here's minus infinity. It's increasing, it's concave down, and it passes through that point. So this is the graph y equals log of x, okay? A very important number would be the value of log of x where, or the value of x where log of x is equal to 1. We call that number e. It's about 2.718. It's an irrational number, so that goes on and on forever. But this is the value log of e is equal to 1. That's how we define e. E is called the Euler number, after the great mathematician Leonhard Euler. It's the L Euler number. Of course, mathematician's name is Leonhard. Go figure. So let's do some examples. Okay, I'm just going to work with. So if y is equal to the log of x cubed plus 1, then what is the derivative of y? So we know the derivative of log is 1 over x, so the derivative of log of x cubed plus 3, or plus 1, is 1 over x cubed plus 1 times, and we have to take the derivative of what was inside, so we get that, okay? So maybe we would write that as 3x squared over x cubed plus 1. Okay. In general, if y is equal to the log of any function, then its derivative is equal to the fraction that looks like that. You take f of x, put it in the denominator, and you multiply by the derivative of fx. This is the chain rule applied to logs. Okay. Let's do another example. So if y is equal to the log of sine of x, I'm going to just connect these with arrows, then y prime, we'll use this rule up above here. It's sine of x in the bottom and the derivative of sine of x in the top. That's cosine, so this is cotangent. Okay. Another example. If y is equal to the square root of the log of x, then y prime is equal to 1/2 times log of x to the minus 1/2 times the derivative of log x. Okay, so what did we do? We wrote this as log x to the 1/2 power, brought the 1/2 down, subtract 1 from the power, and then multiply by the derivative of the log. If you'd like this in a nicer form, which why wouldn't we? This would be that. Okay, simplifying all that, putting it in there. Okay, let's try another one. How about the log of x plus 1 over the square root of x plus 2? Okay, here I want to use a rule of logs to make this a little bit simpler. So let's use the rule about the ratio of log inputs. So this is this looks like this, but then I want to make this even simpler. So log of x plus 1 minus 1/2 log of x plus 2. Okay, and let's take the derivative of this thing instead. This is much easier than taking the derivative of log of this fraction. So we get 1 over x plus 1 times 1, that's the derivative of the first piece, minus 1/2 times 1 over x plus 2 times 1. Notice I'm doing the times 1 because these are the derivatives of x plus 1 and x plus 2. So we get 1 over x plus 1 minus 1 over 2 times x plus 2. So this is the derivative of that in this case. All right, what are we going to do next? Okay, let's do a tiny, well, I have a little more space here. So let's investigate this function. So f of x equals the log of the absolute value of x. Okay, so what is this? This is log of x if x is positive, and it's log of minus x if x is negative. Okay, so the graph of this function will look something like this. It'll go like this on this side, and it will go like this on that side. So it'll just be a mirror reflection here. This is the graph of this function. What is the derivative of this function? So the derivative is 1 over x if x is positive, and it's 1 over minus x times minus 1, which is just 1 over x, if x is negative. Okay? So this function has the same derivative whether or not the x is positive or negative here. So that tells us the following piece of information. So f prime of x is equal to 1 over x, which means that if you wanted to integrate 1 over x, then this is equal to the natural log of the absolute value of x plus c. Okay, so this is the rule for taking the antiderivative of the log function. Let's do an example. So we have, how about x over x squared plus 1 dx. This is a substitution integral. U is equal to x squared plus 1. Du is equal to 2x dx. So what happens to our integral here? It becomes, well, we have a u in the denominator. That 2x, well, the 2 is not present here, so we need a half, right? And then we get du. So we get, okay, a half. The integral of 1 over u is the natural log of u plus c, absolute values, remember, we need absolute values when we're integrating, and so this, it will be 1/2 the log of the absolute value of x squared plus 1 plus c. This is always positive, so we can lose the absolute value symbols, and we could even bring that 1/2 in here as a power. So this is our answer. This function here is the derivative of this function here. Okay, so there's an example of using the antiderivative of log. Let's do another example. How about a definite integral? 1 to e, the natural log of x over x. Okay, another substitution integral, because x in the denominator is 1 over x, which is the derivative of log x. So we take u to be log x, du is 1 over x dx, and that's everything that's in here. So let's rewrite this integral. We have u du. U du accounts for everything in there. Now transform the limits of integration. When x is 1, the log of x is 0. And when x is e, the log of x is 1. right? So this is a much simpler integral to do. It's u squared over 2 from 0 to 1. So it's a half. Okay, so this integral here, whatever the graph of this looks like, the area under it from 1 to e is that. Okay, how about another example? How about the integral of tangent? Okay, this is the integral of sine over cosine. And now we're going to use the logs because cosine, its derivative is almost equal to sine. So let's make that our substitution. Cosine x du is minus sine of x dx. So our integral turns into, pardon me, minus 1 over u du, which is minus the log of the absolute value of u plus c, which is minus the log of the absolute value of cosine x plus c. And if you were feeling really fancy, you could bring that minus 1 in as a power here, and you could get the log of 1 over cosine of x, which is secant of x, if you were feeling fancy. Okay, but let's just move on. All right. That, believe it or not, was section 6.2 star. So 6.3 star is about the inverse function of log of x. So log of x is 1 to 1, so so it has an inverse. Okay, an inverse function. And here's how we write it. We write it as exp of x. So y is equal to the exp of x means that x is equal to the natural log of y. So this is the inverse function to x. So what this means that if you take the log of the exp of x, then you get x. And if you take exp of the log of x, then you also get x. Exponential function, which is what this is, and the logarithmic function cancel each other. Okay, let's look at some properties of exponential function. So the exponential function of 0 is equal to 1, and this is just because 0 is equal to the natural log of 1, right? Use this relationship here. Our y is equal to 1, x is equal to 0. Since the exponential of 0 is equal to, if the exponential of 0 is to be equal to 1, then that's equivalent to this statement right here. So we have the exponential of 0 is equal to 1. The same reasoning tells us that the exponential of 1 is equal to e, because 1 is equal to the natural log of e. Okay, this is all a consequence of our inverse function relationship. Another property we get is that the exponential of any number is e to the r. Okay, and this is because, well, if you take a look, r here is equal to the log of e to the r, which we get just from bringing the r down as a power in front of the log, and this is r. Okay, so we have these properties right here. In fact, these properties make it seem like e and the exponential function are pretty heavily related, and so we make our definition here that e to the x is just equal to the exponential function of x, and this is for all x in R. This is the symbol, by the way, for the real numbers. Sometimes we'll write that symbol for the real numbers. It looks like an R with like a bar. So the real numbers. So for every real number, we define the e to the x to be the exponential of this. So now what does that mean? So another more compact way of writing this relationship here is to say that if you take e to the log of x, you get x, and if you take log of e to the x, you get x. This will be a fundamental relationship for us as we go through this section. Okay, so let's start off with some examples. Find x if log of x equals 5. Okay, solution to this is easy. You just take e of both sides. E to the log of x equals e to the 5. But that's e and log of x cancel each other, so that means that x is e raised to the power 5. Okay. Another example, solve e raised to the 5 minus 3x is equal to 10 for x. Okay. Easy solution here. Just take the log of both sides of this. You get 5 minus 3x is equal to the log of 10. And then you just solve this for x. So you get x is equal to, how about the log of 10 minus 5 over minus 3. Okay? If we were feeling like writing this in a slightly nicer form, then we might write that. We might take that minus sign up. Okay? Great. So that's the solution there. Okay? Let's graph the function e. Okay? We already know what it should look like because we know what the graph of the log of x looks like. This is log of x. It passes through the point 1, 0. It has the y-axis as an asymptote, vertical asymptote. So that means using the fact that graphs of inverse functions to each other are mirror reflections around the line y equals x, that e should look just like a mirror reflection. So this is e to the x here. In particular, some rules about this. As x goes to infinity, e to the x is equal to infinity. As x goes to minus infinity, pardon me, then e to the x is equal to 0. Those are some properties of e to the x. Let's do a really quick example. The limit as x goes to infinity of e to the 2x over e to the 2x plus 1. Okay. How do we compute this? Well, the same way we compute limits for polynomials. Factor out the e to the 2x here, and you get 1 over 1 plus e to the minus 2x. Notice here, e to the 2x times e to the minus 2x. They will cancel each other out. And so that cancels with that. And now, as x goes to infinity, minus 2x goes to minus infinity. And so we use the property that if you take the exponent to minus infinity, you get 0. So this will be 1 over 1 plus 0, so it's 1. Okay, so there's that computation. Let's write down some laws. So 1, e to the x plus y is equal to e to the x times e to the y. 2, e to the x minus y is equal to e to the x over e to the y. And 3, pardon me, e to the x raised to the power r is just e to the x times r. These are our laws for exponents. They're very similar to the laws for logs. Let's investigate the following question. What's the derivative of e to the x? Okay, here's how it goes. Y equals e to the x. So what does that mean? That means the natural log of y is equal to x. That's using the properties of inverse functions, log and e. Now let's take the derivative of both sides of this. On this side, you get 1 over y times the derivative of y. That's the chain rule. On this side, you get 1. So that tells you that y prime is equal to y, and y was e to the x. So that means that e to the x prime is equal to e to the x. So e to the x is its own derivative. Okay, how about that? This is the only function that's its own derivative. Well, up to a constant multiplies. And the rule then for taking derivatives is if you have e raised to any power, any functional power, then you write e to that power, because e is its own derivative, and then you multiply by the derivative of the power. So this is an important rule. Let's do 2 examples of this, and then we'll be done, pretty much. Example, e to the power tangent of x. All right, easy enough. Tangent of x, its derivative is secant squared of x, and so the derivative is e to the tangent x times secant squared. Another example, e to the minus 4x times sine of 5x. Okay, product of things and some chain rules. Okay, e to the minus 4x, its derivative is minus 4 e to the minus 4x. leave the sine of 5x alone, plus e to the minus 4x, and then the derivative of sine of 5x is 5 times cosine of 5x, okay? Easy, easy, easy. Integral of e to the x is its own integral. So we get this. This is the fundamental relationship for integrating, and that is the end of section 6.2 star and 6.3 star.